students. Welcome back to our next topic in our science series. Today we begin a topic which will basically continue into next week as well. But I've divided into 2 week sections, and this week we are going to be talking about weather. Next week we're going to focus on climate. The two are very closely related to one another, but we will begin to see the differences as we explore each of these topics, beginning today with weather. So you may look at this picture and recognize a weather pattern here immediately. This is a picture of a terribly strong weather system known as a hurricane. And you'll notice the eye of the storm in the middle. And of course, this is not a video, it's just a photograph, but you can make out the circulating pattern of the air in the atmosphere. And you wouldn't want to be underneath that particular storm because hurricanes can be pretty strong and pretty deadly. Thankfully, where we live, most of the weather that we experience is a little bit more subdued, you might say, than major hurricanes that are very prevalent in certain parts of the world, like the Gulf of Mexico. Of course, New Jersey, we do get hurricanes from time to time, and a lot of other storms for that matter. But before we diverge too far from our topic, let's get into our notes right now. Yesterday, you were able to check out some videos introducing this topic, some interesting things. And so we're going to explore some of that material and we're going to summarize it here in our notes now. So let's begin with basically a definition of what weather is in the first place. Weather can be defined as the condition of the atmosphere in terms of heat, pressure, wind, and moisture. Now, notice I've bolded some of the words here, beginning with atmosphere. We're going to define atmosphere here in a moment, and we're also going to explore each of these other bolded words: heat, pressure, wind, and moisture. Because in order to understand weather more completely, we really do need to understand each of these individual words in greater depth. So as we continue forward, let's explore this first word a little bit more: atmosphere. The atmosphere of planet Earth is a mixture of gases surrounding our planet. Now, not all planets have an atmosphere. Not all astronomical bodies have an atmosphere. In our solar system, actually, the majority of planets do have atmospheres, but the atmosphere of Venus is way too thick to support life. The atmosphere of Mars is way too thin to support life. But the atmosphere of Earth is just right. It is that perfect blend of not only the types of gases that are in it, but the right concentrations and the right depth. Everything is perfect here on Earth, at least today. In fact, astronomers consider our Earth as being located in a region of space from our star known as the Goldilocks region. And as astronomers around the world are continuing to discover exoplanets or planets beyond our own solar system, they are very interested in searching the Goldilocks regions of other star systems to see if there might be other planets similar to our own planet Earth elsewhere in the galaxy as well as in the universe. Who knows? Maybe there might be another planet similar to our own that harbors life. Perhaps in your lifetime you'll discover alien creatures. But we're getting off the subject here. Let's return to weather at this time. So understand that the atmosphere is a mixture of gases surrounding the Earth. And our last topic, we explored the mixture of gases in our atmosphere, if you recall, and discovered that our atmosphere has about 21% oxygen, which we need to breathe, about 78% nitrogen, which is fixed in the nitrogen cycle, and has a smaller portion of carbon dioxide gas that we breathe out, in addition to water vapor. But those gases are simply mixed together, and we are dependent on that mixture of gases in the right concentrations and with the right air pressure, which we'll talk about more. Now, in terms of things moving around in the atmosphere, we have to mention heat energy. As I've already mentioned, our sun is the closest star to planet Earth. We are revolving on our axis, or rotating on our axis, and revolving in our orbit around our sun, just as other planets are. And our sun is the source of most of the heat in the atmosphere of planet Earth. And as we discover more about weather and we're thinking about the atmosphere, we really have to explore briefly this idea of heat energy and how heat energy moves around, in particular in the atmosphere. But heat can move in different ways. In fact, there are three ways that heat energy is spread in the universe. The first way is called radiation. Now, I know when many people hear the word radiation, they think immediately, oh, bad stuff. We're going to die of cancer from radiation poisoning. And yes, some forms of radiation are deadly if you are exposed to them, even in small amounts. We'll learn much more about radiation and radioactivity when we get to physical science. But the radiation we're talking about here is in reference to the radiant heat energy that is transferred by waves through empty space. You see, we're about 150 million kilometers away from the sun, and there's nothing but empty space between Earth and the sun. But that heat energy that the sun produces has to get here somehow. Thankfully, it travels by energy waves in the form of radiation. So planet Earth is heated through space by the sun with radiation. That's how we get the heat energy in the first place. Now, there's a second way that heat energy can be transferred or moved from one place to another, and that second way is called conduction. Conduction is when you actually touch something. When you make contact with an object that is hotter than you, that heat energy is going to travel from that object to you. Don't ever do this, but if you touched a hot stove, you would get a burn, and you'd be burned because of the heat energy that traveled through you by direct contact. That's called conduction. You touch something hot, you may get burned, or you will feel that heat because of conduction. And conversely, if you touch something cold, like a cold window on a winter day, it'll feel cold because the heat energy is actually going from your hand to the cold window. But heat energy does move through conduction. Conduction is not necessarily all that important in terms of weather. Really, the third way of heat energy transfer is the most important when we talk about weather, and that is called convection. Convection is when heat energy is transferred or moved by a fluid. Now, when we talk about fluids in science class, we're actually talking about both liquids and gases. So, convection takes place in oceans, convection also takes place in the atmosphere. And the interplay between the oceans and the atmosphere are what really generate a lot of the weather systems that exist on planet Earth. There are some exceptions, but by and large, the weather you experience on a daily basis are a direct result of convection. And speaking of convection, there is an interesting effect that takes place with convection that you undoubtedly have heard of before, and it is called the greenhouse effect. The greenhouse effect is impacted by the fact that heat energy from the sun experiences radiation. The heat is radiated toward Earth. Now, if Earth had no atmosphere whatsoever, the sunny side of our planet would be really hot, and the dark side of our planet would be really cold, just like our planet's moon. The moon, which we've learned about before. The sunny side is hot, the dark side is cold because there's no atmosphere to trap the heat energy. So we can actually be thankful for the greenhouse effect because the greenhouse effect enables heat energy to be trapped by the atmosphere. Now, for the most part, this is a good thing because this prevents us from freezing at nighttime. I mean, that would be really bad. So, the heat energy that is radiated toward our planet during the daylight hours is reflected back into the atmosphere, and the atmosphere helps to cover us like a blanket so that even when the light is not shining, namely during nighttime, the atmosphere remains at a survivable, livable, temperate temperature. Not like the wild extremes you would experience on the moon where there is no atmosphere. So the greenhouse effect is a good thing. Now, I know a lot of folks, you hear of the greenhouse effect being a bad thing, and we're going to talk more about that next week when we get to climate. But the controversy has to do with the greenhouse effect and global warming. Again, we'll discuss that in more detail next week. But for our purposes right now, the greenhouse effect is something that takes place simply because we have an atmosphere, and the greenhouse effect in and of itself is not a bad thing. But while we're on the topic of heat energy, we have to explore another part of heat energy before we get into the nitty-gritty details of the finer points of weather. And this involves the shape of our planet. Planet Earth is a sphere, it's like a ball. And so, based on your location on planet Earth and based on the rays of solar light and heat energy from the sun, some parts of our planet receive more direct rays from the sun. Some parts of our planet receive less direct rays from the sun. And this fact of the shape of the Earth enables there to be different temperature regions on our planet. Namely, near the equator, it's going to be hot, hot because of the direct rays of the sun. If you're at the poles, generally speaking, it's going to be colder because the angle of light touching our planet is a much smaller angle, a lower angle, a more acute angle, you might say, which means that more energy is bounced off the surface at the poles than it is at the equator. So we have these global variations of temperature ranges that exist on planet Earth. And it's this interplay of heat energy that is the driving force of weather on our planet. So, with that background information in mind, we're now going to explore some of the different specific components of weather itself. So, are you ready? Here we go. Let's begin with air pressure. Air pressure is the force of the atmosphere pushing on the Earth's surface. Now, how can I illustrate this? Well, hold on a moment. I just got a bear of an idea here, okay? If I'm sitting here right now, all I have above my head is air, and the air is not terribly heavy on me right now. But if a bear came along and sat on my head, I would feel the weight of the bear pushing down on my head. Why? Because that bear has a certain mass to it. It's made up of matter. And that mass will be pushing down on my head, and I'll feel that. Now, we don't necessarily feel the air pressure so much specifically right now, although ask an older person when it's raining if their joints are aching or not. There's a lot of suggestive evidence that implies that some people are very sensitive to changes in air pressure, and they can, quote unquote, feel it in their bones. And I have to say, the older I get, the more I tend to feel it in my bones too. When the air pressure drops, which is related to bad weather like rainy weather, I kind of feel it in my bones. My joints start aching a little bit. It might have something to do with air pressure, or it might just have to do with the fact that I'm getting old. But back to air pressure. So we have an atmosphere surrounding us all the time here on Earth, thankfully, or we would asphyxiate. And there's a certain amount of air that's on top of us. That air is pushing down on us all the time, even though we don't feel it, because our bodies are pushing out all the time with the same pressure. Now, believe it or not, the amount of pressure pushing down on every square inch of your body, that's like the size of your thumb, basically, okay? 14.7 pounds per square inch. That's how much pressure is pushing down on your body right now. Again, you don't feel it because your body's pushing back with an equal pressure. But if you take a gallon of water, that weighs about 7 pounds. Take about 2 gallons of water, and that's about 14 pounds. Imagine those 2 gallons of water are being pushed down on every square inch of your body. That's how much atmosphere is above us. That's how much the atmosphere is pushing down on our bodies right now. It's true. It's true. We are always under a lot of pressure. The higher you go in the atmosphere, the less pressure you're under. The lower you go in the atmosphere, the more pressure you are under. And if you start diving under the water, well, you're under a lot more pressure. We'll talk about that later. Okay, now, so air pressure, what does that have to do with weather? Well, air pressure is dependent upon the density of the air above you. Maybe you've heard the old expression that hot air rises. Well, it's true. Hot air does rise and cold air sinks. The reason for that has to do with density. Cold air is more compact. There are more particles in a volume, and it sinks. Hot air is more energetic. The particles are spread out, less dense, and it rises. That's what enables hot air balloons to fly in the sky. They're less dense than the relatively cool air surrounding them. So air pressure is dependent upon the density of the air. And we have to explore this a little bit further because there are different factors that affect the pressure of the air. And these factors are basically what control weather. So let's briefly explore these three factors affecting pressure. Number one, temperature. In fact, I've mentioned it before, but as temperature increases, air pressure decreases. And again, think of that example of a hot air balloon. The, the higher the temperature, the hotter the air. The hotter the air, the more energetic it is. The more energetic it is, the more spread out it is. And the more spread out the particles, the less there is of it in a given volume, which means it's less dense. Remember, density is equal to mass divided by volume. So the less mass you have in a particular volume, the less dense it's going to be. So factors affecting pressure, number one, temperature. As temperature increases, air pressure decreases. Factor number two, water vapor. Water vapor describes how much moisture is in the air. During wintertime, it's really easy to see water vapor when you breathe on a cold window. All of that condensation is a result of the water vapor that you are breathing out. Now, here's the connection to pressure. As water vapor increases, air pressure decreases. Now, this may not seem like it makes a lot of sense at first until you realize that water vapor and its concentration is also partly dependent upon the temperature of the air. Warmer temperatures allow more water vapor to exist in the air. So when there's more water vapor, when water vapor increases, that's also indicative of warmer air, and warmer air rises, and rising air is less dense. Because when the temperature goes down, when it gets colder, water vapor changes state into precipitation. It'll rain. And so the converse will be true there as far as the connection and relationship between water vapor and pressure. What you need to know right now is that as water vapor increases, air pressure decreases. And now let's finish up with the third factor affecting air pressure, and that is altitude. Altitude on Earth is usually described as elevation. If you're on the surface of the Earth, like climbing a mountain, you refer to your change in elevation. If you're in an airplane flying above that mountain, you usually refer to altitude. But for our purposes, altitude and elevation are basically the same thing. And here's the deal. I want you to picture climbing this mountain here. Picture yourself climbing this mountain. The higher you go in the atmosphere, you have more or less atmosphere above your head, the higher you go. You're going to have less. So as altitude increases, air pressure decreases because there's less air on top of your head and the rest of your body for that matter. So the higher you go in the atmosphere, the lower the air pressure because there's just less air on top of you, which means the lower you go as altitude decreases, air pressure increases. The highest air pressures on Earth are those that are at the lowest elevations. So understand this connection between altitude and pressure. And actually, our last slide for today is the instrument that measures air pressure. Talking a lot about air pressure today. Very important in understanding how weather works, which we're going to get into more tomorrow. But for now, let's finish with this instrument that measures air pressure. How do we really know whether air pressure is increasing or decreasing or staying the same? It's called a barometer. A barometer is an instrument that measures air pressure. And it's that change in air pressure that results from uneven heating of the Earth's atmosphere that drives the force of weather. And so tomorrow we're going to pick up where we left off here, and we'll begin with wind with tomorrow's lesson. But for now, I'm going to say bye-bye.